Hello students, our next topic of discussion is equipotential surface. As the name indicates, the surface at every point of which the potential remains constant, that surface is called equipotential surface. So the charge distribution may be of any type. So how we can define a surface at every point of which the potential due to charge distribution is the same is called equipotential surface. So the surface at which the potential remains constant is called equipotential surface. Now let us see how we can draw the equipotential surfaces. First, let us try to draw for the uniform electric field. We know that the uniform electric field is represented by the parallel lines, and how we can draw the equipotential surfaces. You can see here, this is first equipotential surface, this is second equipotential surface, and this is a third equipotential surface. So how we have to draw the surfaces? We need to draw the surfaces perpendicular to the field lines. Those surfaces would be the surfaces at which the potential will remain constant. Now how we can draw the equipotential surface for the isolated point charge? We know that for point charge the potential is what? That is kq by r. Q is one isolated charge, so it is constant. K is already constant, and if I am able to make R constant, then I would be able to get the equipotential surface. So what type of surfaces I will get for an isolated charge? So these are the field lines, and you can see here, for making R constant, I will get the concentric spheres. So at every point of the sphere, the value of R would be constant. So you can consider any point. This R will remain constant. So this particular sphere is an equipotential surface for this charge plus charge which is lying at the center of the sphere. So any of the sphere you can consider to be the equipotential surface, because the radius for every sphere is constant. So every sphere is having no doubt different potential, but for one particular sphere, the potential on the surface of the sphere is constant. So all these concentric spheres are the equipotential surfaces for an isolated charge. Similarly, we can draw the equipotential surfaces for dipole and for the charge distributions also. So let us see, I'm taking this clip of your NCERT. You can see here the equipotential surfaces for the dipole. So plus charge and minus charge, two equal and opposite charges, and you can see how we can draw the equipotential surfaces, two concentric spheres, but their shape is little bit different. And similarly here, you can see for two positive charges, how we can draw the equipotential surfaces. These are the equipotential surfaces for the two positive charges. And you may get a question to draw the equipotential surfaces for a point charge, for uniform electric field, and for two charges, combination of the two charges, they may be same charges, positive, negative, or they may be different charges as in case of dipole. So in both of the cases, in all the cases, we need to draw the equipotential surfaces. So we can draw the equipotential surfaces. So this we have already discussed. Now let us discuss the properties of the equipotential surfaces. What are the different properties of equipotential surfaces? First, very important property of equipotential surfaces: no work is done in moving a test charge from one point to another on an equipotential surface. So here work will not be done. For example, we are moving a charge on the surface of equipotential surface. Then we know that the work done is charge into the potential difference. So if potential difference is 0 for equipotential surface, there is no difference in the potential. Potential is constant everywhere. So work done would be 0. So this formula you can see here. we know that potential difference between the 2 points B and A, how we can define it? This is the work done in moving the charge from A to B per unit charge which we are moving. Now for the equipotential surface, VA and VB are equal. So this change in potential would be 0 for the equipotential surface, and so in that case work done would be 0. It means no work is done when we move a charge on equipotential surface. If no work is done, then no change in kinetic energy will take place when we are moving a charge on equipotential surface. No change in its speed, no change in its kinetic energy, no work is done. So these are very important property. This is very important property for equipotential surface. Now let us see the second property. The electric field is always perpendicular to the element dl of the equipotential surface. Or in other words, we can say electric field lines are always perpendicular to the equipotential surface. As we know that no work is done on equipotential surface. So as from the definition of the work done in moving a charge on the surface having electric field, we know that work done is what? This is negative integration of electric field, dot product of electric field and small distance. So work done is 0. If work done is 0, E dot dl would be 0 or E dl cos theta is 0. But E and dl, they are not 0 here. So cos theta has to be 0 or theta is equal to 90 degree. So we can see here electric field and dl are perpendicular. Electric field and dl is what? dl is a distance moved on the equipotential surface. So both of these two things are 0, or in other words, we can say electric field and equipotential surface are perpendicular. So this is the proof. For this property, electric field is always perpendicular to the equipotential surface. Third property is equipotential surface indicates regions of strong or weak electric fields. So with the help of the equipotential surfaces, we can draw the regions of strong electric field and weak electric fields. We know that electric field is defined as the negative potential gradient from the last definition also. We can see here, we can show here that electric field is negative of dV over dr. So dr is equal to dV over E, but dV is constant for equipotential surface. So dr is inversely proportional to electric field. Since if electric field is strong or large, dr would be same because it is inversely proportional to this. If this E is large, dr would be small. Means here dr is what? Dr is a separation between the two equipotential surfaces. So if electric field is large or strong electric field is there, then the equipotential surfaces would be lying closer to each other because dr here is small, and vice versa. So for the strong electric field, the equipotential surfaces are crowded or they are lying closer to each other, and for the weak electric field, dr would be large, means equipotential surfaces, they would be lying away from each other. So next property is two equipotential surfaces cannot intersect. And we already know that as the two electric field lines cannot intersect, because at the point of intersection, the electric field would have two different directions, which is not possible for a vector quantity to have two different directions at one point. Similarly, we can prove that two equipotential surfaces cannot intersect. If the two equipotential surfaces intersect, then at the point of intersection, there will be two values of the electric potential, which is not possible for equipotential surface. For equipotential surface, there is one value of the potential. So, two equipotential surfaces cannot intersect. So, here some note is that electric potential is a scalar quantity, whereas potential gradient is a vector quantity. We know that potential is what? This is the work done in bringing the unit charge from infinity to a particular point. But potential gradient, you can see from here, potential gradient is what? This is equal to the electric field. So, and we know that electric field is what? This is a vector quantity. So, potential gradient is a vector quantity. Electric potential at a point is a scalar quantity. And why this negative sign is there? What does this signify? The negative sign of potential gradient shows that the rate of change of potential with distance is always against the electric field intensity. So, the rate of change of potential is always opposite to the electric field intensity. So, these are some of the properties of equipotential surfaces. So, that's all for this topic. Thank you.